What is up, guys? We're back with another Leetcode question. Today we're doing problem 16 and 17, count subtrees with max distance between cities. There are n cities numbered from 1 to n. You were given an array edges of size n minus 1, where edges I is from U to V, represents a bidirectional edge between cities U and V. There exists a unique path between each pair of cities. In other words, the cities form a tree. A subtree is a subset of cities where every city is reachable from every other city in the subset, where the path between each pair passes through only the cities from the subset. Two subtrees are different if there is a city in one subtree that is not present in the other. For each d from 1 to n minus 1, find the number of subtrees in which the maximum distance between any two cities in the subtree is equal to d. Return an array of size n minus 1, where the dth element, 1 index, is the number of subtrees in which the maximum distance between any two cities is equal to d. Now, the distance between the two cities is the number of edges in the path between them. This explanation is a little confusing, but the answer just clears everything up. The example just clears everything up. So we have this n, and we have our list of edges 1, 2, 2, 3, and 2, 4, and this is how the graph will look like. The output is 3, 4, 0, y, because if you look at index 0, and we're going to say it's 1 base, so I'm going to use 1 base language from now on, right? So we're going to look at index 0, which is 1, right? And so all the subtrees that have a maximum distance of 1, we can get 3 of those, meaning we go from 2 to 3, 2 to 4, and 1 to 2. Right? So 1 and 2 is a subtree, 2 to 3 is a subtree, and 2 to 4 is a subtree. And each of those have a maximum distance of 1. So we have 3 of those, we'll put 3. As for the subtrees that have a maximum distance of 2, we get 4 of them. Why? We get 1, 2, 3, 1, 2, 4, 4, 2, 3, and 1, 2, and 3, 4. 1, 2, 3, 4. See, 1, 2, 3, 4. And so those would have a max distance of 2. As for the ones that have a max distance of 3, we don't have any, so we'll just return 0. Okay, so how are we going to approach this problem? Well, we'll look at the hints, and the hints basically kind of clear everything up. So we know now we want to find the subtrees, and we want to find the maximum distance for each subtree. So we're going to split this problem into 2 steps. One is finding all the possible valid subtrees. Okay, let's do it like this. One is finding all the possible valid subtrees, and the next part is finding the maximum distance in each subtree, okay? So finding all the possible subtrees, that's 1. 2, finding max distance in each of those subtrees, right? Okay. So that's that. So we have those 2 steps. Now, how are we going to find all the possible subtrees? Well, we're going to use a bit mask. Why can we use a bit mask? Well, we know the maximum number of nodes will be 15. Okay. So we can use a bit mask where bit I is set if I is included in the subtree, meaning that if I is part of the new subtree, then we'll say it's included. Okay, so it's going to be a bit mask of 15 bits, right? And if it's 0, that means that node is not included in the subtree, and if it's a 1, it's included in the subtree. But now, how do we know that's valid? Because sometimes we can have 2 nodes that are included in the subtree, but there's no path between them, right? There's no direct path between them. There's no path between them because other nodes are not included. There could be a direct path between them if we took the entire graph, but because the other nodes are not included, and these are the only 2 nodes in the current subtree, there's no path between them right now. So we have to make sure that it's a valid subtree. And the way we're going to do that is we're going to do maybe a DFS and travel from one node, right? And find all the possible nodes that we can visit from there, right? We're going to do it as from one node and count the number of nodes we can visit, right? So if I start at this node and I count the number of nodes I can visit, right? In this example, we have 2 nodes. There's no path between them right now, and the subtree only has 2 nodes. So if I start from one node, how many nodes can I visit from there? None, right? Because there's only one other node in the subtree. That's this one, and there's no path between them, so we can't visit anything. So we'll start from DFS from one node and count the number of nodes we can visit, and we'll get a number. And if that's not equal to the number of bits that are set in our bit mask, then we return false. Okay? Then we return false because this isn't a valid subtree. So if the count of nodes that we can visit from one node in the subtree is not equal to the number of set bits in the mask, then it's not valid. Okay, that's how we're going to find the all the possible subtrees and make sure they're valid. Now, how are we going to find the max distance in each of these subtrees? Well, we're going to use something called finding the diameter of the tree. What's the diameter of the tree? Well, it's the length of the two longest paths, basically, from the roots, or the length of the two. It's the nodes that have the two highest height, the two longest height. Okay, or the depth. Sorry, the two highest depths. The depth, right? Yeah, it's depth. So, for example, we have a root node in our tree, and then one branch, maybe one path all the way down to a leaf node, has a depth of like 5, and the other one has like a depth of 3. Okay, the second longest one has a depth of 3. So we'll say our diameter in that case is 5 plus 3, which is 8. And in this case, we'll also add another 2, we'll make it 10. Okay, so we'll say in this case, the diameter is, let's just say, 10. Okay? Because to go from one leaf to kind of like, let's say the next leaf, I guess. Yeah, the next leaf, I guess. The longest path from one leaf to another leaf, that would basically be your diameter. And you can Google what is the diameter of a subtree, and it'll probably explain it a little better. So the diameter of the length is the length of the longest path from the root, and that would plus the length of the second longest path from the roots to a leaf. Okay? And so this would give us the maximum distance. That's how we find the maximum distance of a subtree. Okay? So that's all it is. It's basically finding out, realizing that it's kind of like we're going to have to take a brute force approach. One, we're going to have to find all the possible subtrees, and for each of these possible subtrees, we just want to find the maximum distance. And every time we get a max distance in this subtree, we're going to increment our answered array by 1 at that index. So for example, we're going to create this array. We have n is 4, so we know we're going to return an array of size 3, which is always going to be n minus 1 because of the problem constraints, right? Obviously, return array of size n minus 1. And then every time we get a maximum distance of any of our possible subtrees, we'll increment that index. So for example, if our maximum distance is something like, I don't know, 3, and then we'll increment the second index. If our maximum distance is 1, we'll increment the 0th index. In this case, the 1th index, so I guess the first one, but I'm speaking in 0 index terms, right? So if our maximum distance is 1, we'll increment this one by 1. For maximum distance 2, we'll increment this one 1. For maximum distance for the subtree is 3, we'll increment this one by 1. So that's how we're gonna approach this problem. Now let's go through the solution. Okay, here's the starting. Okay, we're gonna create our answer array, which is an array of size n minus 1. This is a field variable for the class, and it's variable in the class. We're gonna create an array of vertices. Okay, these are all our nodes. Every vertex has neighbors. As I is basically the number of that node. It's going to have a height. It's going to have the diameter. Okay, diameter meaning starting from that subtree, the diameter from there. Okay, the diameter of the subtree that starts at this vertex. So we create an array of vertices. We fill them up. We add new vertices here. Then we're going to go through all our edges. And we're going to use our edges to start setting up our vertices. Meaning, we're going to grab the first node, the second node, and we're going to add them, we're going to make them neighbors to each other. So this is doing. And we do this again for some reason. Then we call this brute force approach. Here's our brute force. We have all the vertices. Okay, it takes in all the vertices. It takes in the current vertex we're at, and it takes in the bit mask. What is this bit mask again? What did we say? The bit mask is going to be the number of included nodes in our current subtree. Okay, the number of included nodes in our current subtree. And now basically what we're trying to do with this bit mask is we're going to get we're going to create all possible subsets of this mask. Okay, all possible combinations of zeros and ones with this mask. How does this work? Well, ignore this for now. What we're going to do now to generate all possible subsets of this mask is these lines, line 63 and 64. We're going to keep calling this brute force function recursively, and every time we call it recursively, remember, we can either take two paths, right? If there's 15 possible nodes, they can either set or not set. That means we have 2 to the 15 possible subsets. Why? Because at every step, we can either include the other node or we can not include another node, and we can skip past it, right? So we can either include the node or we can skip past it, or we can include the node or skip past it, or we can include a node or skip past it, okay? So I can include 1, and then I can check the subtree of 1, and then once I'm finished with 1, I can include 2, or I can skip 2 and just do 1 and 3. Or I can do 1 and 2, right? And then from 1 and 2, I can either do 2 and 3, or I could just do 1 and 2, and then skip the 3, and maybe if there's something else here, I can do that. So then let's just say we start back from 1. Instead of going directly to 2, I skip 2 and I do 3 instead, so I have 1 and 3. And then from 3, I can go to 4, or I can skip 4. So that's how we're going to generate all our possible subsets, and that's what this is doing. I plus 1 is basically saying, okay, move along, skip it. Oh, sorry, it's saying basically move along to the next step. That's what I plus 1 is doing, move along to the next node. And then this and this, what this is doing is like mask, and we're ORing it with 1 shifted I times, is basically saying, okay, include this node now, include this node. And what this is doing where we don't include this node, because this is going to set that a bit, what this is doing is saying, okay, don't include it, let's skip past it. Okay, so we're going to either include it or skip past it. And this is going to create some kind of tree of recursive calls. And at the end of it, we'll always hit I equals to n. Okay, and then we're going to run this. Now what is this doing? What this is doing is basically now we're going to go through all the once we generated the subset, once we reach the end of this current subset, we're going to run this part over here. Okay, what this is doing is basically, I'm just checking the time, it's basically going through all the nodes and it's checking for this node at E, is the bit set, meaning is it included in our subtree? That's what this is doing, right? We're saying 1 left shifted all E times, and we're ending with the mask. So that means we're checking what if this node is included in the mask, and it's also included. I guess the 1 left is shifted E. If that bit is set, so if that bit is set, that means this node E is included. Okay. If it's not equal to 0, meaning if it's not included, then don't do anything because that node is not included. But if it is included, then we need to do some checks. 1, we're going to grab the count of the number of nodes in the subtree. Okay, we're going to grab the number of nodes in the subtree starting at this E. Okay, then what are we going to do? We're going to check if it's equal to our mask, as we mentioned, right? How do we validate? Well, we're going to deduct from 1 node and count the number of nodes we can visit, and then the count of nodes equals to the nodes in the subtree is not equal to some of the bits, then it's not valid. If it is, then we're good. That's what this is doing. This is going to be basically this count function right over here. Let's go really quickly. It's going to be that DFS that grabs all the nodes in the subtree. Okay. If what is all this doing is basically checking if that current node, right, that bit is set in our mask, meaning it's included in our subtree. So if it's not, we'll just return 0, meaning it's not included. Else, we'll start with C is equal to 1, meaning our current node, so our size is 1. And we'll go through all the neighbors. We're checking the previous, meaning because we don't want to go back to the parent. We'll skip past the parent, and then we'll keep adding the count recursively. So this is basically a really simple DFS to count the number of nodes in the subtree to see all the nodes we can visit from the current node. Now, if the count is not the same as the number of set bits in our mask, that means it's not a valid subtree, so we'll skip past it, we'll return. If it is, then we call this diameter function, which will basically, diameter method, which will set the diameter of this vertex. Okay, it will set the diameter of this vertex. How does this diameter method work? Remember, what is the diameter calculating? It's calculating what? The maximum distance of the subtree. So now we validated that this is a proper subtree. Now we need to calculate the diameter of this subtree, as we mentioned in our steps. Remember, just keep track along with these steps. We're just following through these steps now. So let's grab the diameter. Once again, we're checking if this bit is set. If it's not set, then the height is obviously -1, diameter is -1, we'll just return. If it is, we'll set the max 1 and max 2 to both -1. What is max 1 and max 2? What are they going to be? Well, max 1, as we mentioned, what is the diameter? It's the length of the longest path from the root to a leaf plus the length of the second longest path from root to leaf. Max 1 is the longest path from root to leaf. Max 2 is going to be the second longest path from root to leaf. This is the diameter, the maximum diameter we're going to get. We're going to start at this node. We're going to travel to all our neighboring nodes. Okay. Once again, we're skipping past our parent. And for each of our neighbor nodes, we're going to calculate the diameter for them as well. Okay, we're going to DFS down, grab diameter of subtrees of the current subtree. The above call will set the height of other. Okay. And then what we're going to do now that other's diameter will be set, because this is what diameter method is doing, right? It's setting the diameter of cur. Once it gets set, what we're going to do now is this. It's also going to set the height. So if the height of this current neighbor, right, is bigger than our maximum, what? Then we set our maximum to basically we're going to set, let's do this one first. We're going to set our, actually do this line first. That makes no sense. So if the height of the neighbor is current than our biggest maximum, that means what? That means that means the neighbor now will be the maximum and the previous maximum will be the second biggest. So we'll make the previous maximum the second biggest, that's what this is doing. And then we'll make the maximum our current neighbor's height. Else, if it's only bigger than the second maximum, then we just make the second maximum the other's height, right? The neighbor's height. And then once again, we need to keep track of the current biggest diameter of the neighbor. And that's what this is doing. We use the previous one or we use the neighbor's one, the current one we're at, right? For other. Once we do all this, we can finally set our current height to, because it's just going to be the maximum height of one of these subtrees plus 1, since we're one node above this tree of our subtree. So we'll just add 1. The diameter is similar, right? We'll get the maximum on the left. Remember, what is the diameter? The maximum longest path from root to leaf plus the second longest path from root to leaf. The longest path from root to leaf plus the second longest path from root to leaf. Or it could be the diameter of one of our subtrees. Okay? And if it's in this case, if it's the longest path from the left plus the right, we also need to add 2y. I wrote it right here. Curve's diameter is the diameter of one of the subtree, the length of 2, max path downward plus 2. We added plus 2 since an extra 2 steps it added. For example, from left node up to the current and then down to right node. Because we added one node above these two subtrees to connect it. So let's say this was our left subtree, this was our right subtree. Now our root node is right over here, right? We get the height of this one and the height of this one. But now we need to connect these two. So we go up 1 to the root and then down 1. So that will add 2 extra steps. The length will increase by 2. And that will give us our current diameter. That's how the diameter is working, aka the maximum distance. That's how that method is working. So once again, we set the diameter of this vertex. We're coming back here. Remember, we're going through all these possible subtrees. We're checking if it's a valid subtree. If it is, we grab the diameter, maximum length, and then we're just checking if the diameter is greater than 0. Well, then we'll increment it to our answer. That's what this is doing. Because the array is 0 index, we're just going to subtract 1. We get the diameter, subtract 1. And just increment it. We found another answer, great. Remember, we'll just increment this one in this case, or this one plus 1. And then we'll return over here, we'll also return. And then we do that for all of the possible combinations of subsets of the trees. And so then eventually our answer array will be filled up. Once that happens, we're done, and then we return the answer. That is the solution for this problem. I hope you guys enjoyed. This is number 1617. Count subtree, the maximum distance between cities. Please subscribe. Let me know if I can improve these solutions in any way. Yeah. Also, just as a side note, this is really, really, really good answer. That took 1 millisecond. This one took 20 milliseconds. 1 millisecond. I found it here. Some guy did it. I don't know how. It's crazy. I tried spending some time understanding it. I might come back and try to figure it out later. Was this crazy? I think it's just like an n to the 5 solution. This one is 2 to the n times n solution. This one is some crazy DP approach. I don't even know what's going on, but it's super fast. Look at these answers. It's crazy. I mean, I don't think this is updated because mine's at like 20 milliseconds, but look here. Look at these. Crazy. Oh, this isn't exactly mine. Obviously, this is from one of yours too. Right here, one of these answers. But this is just crazy. I don't know how this guy got to 1 millisecond. If you guys do understand that solution, please leave it in the comments below. Thank you guys for watching. I'll see you guys in the next video.